The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, in the last lecture, we introduced the Z-transform. In this lecture, I'd like to go backwards. That is, I'd like to introduce the inverse Z-transform and demonstrate some of its properties with a few examples. To begin with, let me remind you of the Z-transform relationship as we talked about it in the last lecture. The Z-transform x of z of a sequence x of n is given by the sum of x of n times z to the minus n. The inverse Z-transform, of course, is the relationship or the set of rules that allow us to obtain x of n, the original sequence, from its Z-transform x of z. There are a variety of methods that can be used for implementing the inverse Z-transform. Some of them are somewhat informal methods, and others, one in particular, which we'll talk about, is a somewhat formal method. To begin with, an informal method, and a method that, in fact, most of us tend to use the most often, is a method that we could refer to as the inspection method for computing the inverse Z-transform. Basically, the inspection method says if we've computed a Z-transform from a sequence, then by looking at that Z-transform, we can recognize more or less by inspection the sequence that that Z-transform came from. For example, we have worked several times now the computation of the Z-transform of an exponential sequence, which is a right-sided sequence, and gotten as the answer, or as the Z-transform, 1 over 1 minus a z to the minus 1 with a region of convergence for the magnitude of z greater than the magnitude of a. Consequently, having worked that example, if I now present you with this Z-transform and ask you what sequence generated it, one way of doing that, obviously, is by inspection, by recognizing that this sequence generates that Z-transform. Another example that we've worked several times now is the exponential sequence which is left-sided, that is 0 for n greater than 0, generating the same ratio of polynomials as in the right-sided exponential, but with a region of convergence which is the interior of a circle, rather than in this case where the region of convergence is the exterior of a circle. And in fact, it was the comparison between these two Z-transforms that caused us to focus in the last lecture on the importance of the region of convergence. So this is one method, which I emphasize again is, in fact, one of the most common methods. That is just simply recognizing the Z-transform as something that we've computed previously from a sequence. And obviously, also, as you work more examples, you build up a larger list of sequences and Z-transforms, pairs which you can recognize. The second method for computing the inverse Z-transform is based on the fact that the z-transform relationship is basically a power series in z. That is, if we look back here at the z-transform expression, this is essentially a power series relationship which expands x of z in powers of z. Consequently, given a z-transform, if we can expand it in terms of powers of z, then we can pick off the coefficients in that expansion as values of the sequence x of n. For example, let's take the sequence, the z-transform x of z, which is 1 over 1 minus a z to the minus 1, or we can rewrite it as z over z minus a. Now, this, of course, is a z-transform that a z-transform whose inverse we know how to compute by inspection. However, we can also compute the inverse z-transform by expanding this expression in a power series. Let's divide 1 by 1 minus a z to the minus 1, and then recognize the coefficients in that expansion as values of the sequence x of n. So carrying that out, we have 1 divided into 1 is 1. Multiplying back, we have 1 minus a z to the minus 1. Subtracting, we then have a z to the minus 1. Dividing by 1, we then have a times z to the minus 1. Multiplying down again, we have a z to the minus 1 minus a squared z to the minus 2. Subtracting, we have a squared z to the minus 2. Dividing by 1, we have a squared z to the minus 2. And if we continue this, we'll generate terms 1, a times z to the minus 1, a squared times z to the minus 2, a cubed times z to the minus 3, etc. This series will continue with an infinite number of terms. And we can recognize then this as the expansion of x of z in the form the sum of x of n times z to the minus n. Consequently, we can recognize that apparently x of n is 1 at n equals 0, a at n equals 1, a squared at n equals 2, a cubed at n equals 3, etc. Of course, there are lots of ways of expanding a function like this in a power series. For example, if I simply reversed the order of these two terms and carried out the division, this isn't the series I'd get. What I'd get instead is the series, which is minus a to the minus 1 times z, minus a to the minus 2 times z squared, minus a to the minus 3 times z cubed, etc. In that case, if this was the expansion, then what I would have to recognize as the sequence corresponding to this is the sequence which is 0 at n equals 0. It has no terms of the form z to the minus a positive power, so apparently it's all 0 for n greater than 0, and it's minus a to the minus 1 at n equals minus 1, minus a to the minus 2 at n equals minus 2, etc. So in fact, for this example, I could expand this either in this power series or I could expand it in this power series. Well, which power series is the right power series? We know, in fact, that given just this ratio of polynomials, there are several choices for the sequence that it corresponds to depending on the region of convergence. If I associate as the region of convergence the magnitude of z greater than the magnitude of a, then it's this power series that converges, and this power series diverges. So for that region of convergence, that is, with the magnitude of z greater than the magnitude of A as the region of convergence, this is the power series, and consequently the answer is a to the n times u of n, which of course is consistent with what we know already, or equivalently consistent with the inspection method. On the other hand, if the region of convergence was the magnitude of z less than the magnitude of A, then it's this power series that converges, and consequently, in that case, we get a left-sided sequence, which again is consistent with what we know either from the inspection method or equivalently from the examples that we've worked before. One obvious drawback to the power series is the fact that when we generate the inverse Z transform this way, we get the values in the sequence as individual terms. That is, we generate x of n not in closed form. We generate it as a sequence. For simple sequences, of course, we can recognize a closed form for that, but in more complicated cases, we can't. All right, a third method for generating the inverse Z transform is basically an extension of the inspection method, which allows us to take a more complicated Z transform expression and expand it out in terms of terms that we can recognize by inspection. And this method I'll refer to as the method based on the partial fraction expansion. I assume that some of you are familiar with the partial fraction expansion in general for a rational function, but in case you're not, or in case you're rusty on it, let me just quickly review what the partial fraction expansion consists of. Let's consider a general function of a variable, I'll take as a complex variable, x, which is a rational function in x. It is one polynomial in the numerator divided by a denominator polynomial. And let me remark incidentally that you shouldn't confuse this x with the sequence values x of n that we've been referring to. This is simply some arbitrary complex number or complex variable. Now, I can, in general, expand a rational function in terms of an expansion of a form which, at least under certain simple conditions, is a sum of terms of the form of a constant, r sub k, divided by x minus x sub k, where the x minus x sub k's are the roots of the denominator polynomial q of x. And these coefficients are referred to as the residues. Now, to expand this rational function in this form without additional terms, I need to apply the restriction, which I'll do for the purposes of this lecture, that the order of the numerator polynomial is less than the order of the denominator polynomial, and that in addition, there are no multiple order roots of the denominator polynomial. In other words, if the denominator polynomial is nth order, then the n roots of the denominator polynomial are distinct. In the text, there is the more general discussion of the partial fraction expansion when the order of the numerator is greater than or equal to the order of the denominator, or if there are multiple order roots. The essential ideas, of course, don't change. It's just the mechanics of implementing the expansion and the form of the expansion. So for this lecture, we'll assume that the expansion simply has terms of this form. And this then is referred to as the partial fraction expansion of f of x. Now, how do we get the coefficients r sub k in the expansion? Well, essentially by recognizing that if we multiply f of x by one of the denominator factors, say x minus x sub r, and evaluate that product at x equals x sub r, then relating that to this sum, as I've indicated here, when k is equal to r, these two factors cancel out. When k is not equal to r, then when I substitute x equals x sub r in here, then this term vanishes. So basically then what happens inside this sum is that the term inside this sum is equal to 0 for k not equal to r, and it's equal to capital R sub r, that is the residue at the pole x equals x sub r when k is equal to r. So consequently, there's only one term left in this sum, which is capital R sub r, and therefore the residues, that is capital R sub r, can be obtained by multiplying f of x by x minus x sub r, evaluating the result at x equals x sub r, and the resulting number is the residue of f of x at the pole x equals x sub r. That's for the case of simple order poles, that is first order roots of the denominator polynomial, and also for the case when the order of the numerator polynomial is less than or equal to the order of the denominator polynomial. And just store away for later, because I want to refer back to this point, that in particular when there are multiple order poles, the evaluation of the residue is somewhat more complicated. In particular, it involves computing some derivatives, etc. And the higher the multiplicity of the pole, the more complicated it is. And that's a point that will sneak back at us toward the end of the lecture. Now, this, of course, is for a general rational function. Let's apply this now to the inverse z transform. Well, we know that the z transform, well, let's restrict ourselves to the case where the z transform is a rational function of z, or z to the minus 1. And consequently, we can, referring back to the general notion of the partial fraction expansion, either think of the variable z as what we were calling x over there, in which case we have an expansion of the z transform in the form of the sum on k of a sub k divided by z minus little a sub k, where the little a sub k's are the poles and the capital A sub k's are the residues. Alternatively, if we interpret z to the minus 1 as x, then we can expand x of z in the form of some other residues, b sub k, divided by z to the minus 1 minus some coefficient little b sub k, or we can rewrite that as capital B sub k divided by 1 minus a sub k z to the minus 1. So here we're expanding in terms of, we're treating the z transform as a rational function in z. Here we're treating the z transform as a rational function in z to the minus 1. And so what does the method consist of? Well, the method consists of expanding x of z in terms of simple terms like this, and then using the inspection method to recognize what the inverse z transform is for each of the individual terms. To get the final sequence, then, we add those up. That is, we've expressed the z transform as a sum of simple factors. So the sequence, the original sequence, we can express as the sum of the inverse z transform obtained by the inspection method of each of the individual factors. All right, let's just work a simple example to show you what the mechanics are of this and how it works out. Let's take an example where x of z is 1 over 1 minus a half z to the minus 1 times 1 minus a quarter z to the minus 1 with a region of convergence which I'll take as the magnitude of z greater than a half. This has two poles, of course, one at z equals a half, the other at z equals a quarter, and the region of convergence is outside the outermost pole, so what we expect to get is a right-sided sequence. And let's work this one by treating the variable x in our previous discussion as z to the minus 1. And obviously it doesn't matter which one we use, although it turns out actually that depending on how you pick it, you either end up with a numerator polynomial whose order is greater than the denominator polynomial or the other way around. Okay, well, so we want then to expand this z transform in terms of a sum of factors, and let's just rewrite this to make things a little clearer by multiplying denominator and numerator by 2, by minus 2 rather, and then also by minus 4, we can simply rewrite this as 8 divided by z to the minus 1 minus 2 times z to the minus 1 minus 4. So that it's more in the form of x minus a constant times x minus another constant. All right, well, so here then we have the z transform that we want to expand in a partial fraction expansion in terms of treating z to the minus 1 as the complex variable x in the expansion. We have two poles, two roots of the denominator polynomial, one at z to the minus 1 equals 2, the other at z to the minus 1 equals 4. So we need to calculate the residues at each of those roots. To calculate the residue at z to the minus 1 equals 2, what are the steps? Well, we multiply this by z to the minus 1 minus 2, that is x minus 2, where x we're interpreting as z to the minus 1, and then evaluate the result at z to the minus 1 equals 2. Well, obviously, of course, this term cancels out that term. And we want to do that before we substitute z to the minus 1 equals 2. And then substituting z to the minus 1 equals 2, we get minus 2 left over in the denominator, divided into 8, and that's equal to minus 4. So the residue then at z to the minus 1 equals 2 is equal to minus 4. Similarly, to calculate the residue at the root z to the minus 1 equals 4, we multiply by z to the minus 1 minus 4. Then these two terms will cancel out. Evaluate the resulting expression at z to the minus 1 equals 4. So we have 4 minus 2 is 2 into 8 is 4. And the residue then at z to the minus 1 equals 4, the residue is equal to 4. Consequently, the partial fraction expansion for x of z, for this x of z, is minus 4 over z to the minus 1 minus 2 plus 4 over z to the minus 1 minus 4. Well, finally, let's just put this back in a form that is more the form that we're used to looking at the z transform in. In particular, multiplying this piece, numerator and denominator, by minus a half, we get 2 over 1 minus a half z to the minus 1. Here, multiplying numerator and denominator by minus a quarter, we get minus 1 over 1 minus a quarter z to the minus 1. And now we've broken x of z into a form that allows us to use the inspection method That is, we can recognize from this, remember that the region of convergence was outside a circle, so we want to interpret the region of convergence to be the same here. So consequently, for this piece, we end up with 2 times a half to the n times u of n. That's an n. And for this piece, we end up with minus 1 times a quarter to the n times u of n. So by breaking x of z into a sum of components, simple terms, we were then able to apply the inspection method to each one of those to get the resulting z transform in a closed form expression, or at least the sum of some closed form expressions. All right, so that then is basically an extension of the inspection method. When the inspection method by itself doesn't work, it's usually the partial fraction expansion method that one uses, perhaps also in conjunction with some properties of the Z transform, which is something that we'll be going into more in the next lecture. Now, finally, there is a somewhat more formal way of evaluating the inverse Z transform. And in some cases, it's important to actually use this to explicitly evaluate the inverse Z transform. In other cases, it's important to make reference to the more formal inverse Z transform relationship to discuss properties of the inverse Z transform. So sometimes the formal inverse Z transform is computationally useful. In other cases, it's useful in proving theorems or developing properties or something of the sort. Well, this method, the final method and the most formal method, is the method that I refer to here as contour integration. And let me basically hand it to you. That is, rather than go through a derivation, let me just simply state what the inverse Z transform relationship is. In the text, there is a derivation of this. And so for the purposes of the lecture itself, let me just present it. Any objections? No. So, and then also work through at least one example to show you what the mechanics are. It's another nice thing about videotape lectures. There are never any objections. Okay, well, here it is. This is the inverse Z transform. And what does it say? It says the sequence x of n is 1 over 2 pi j times a contour integral, which I'll return to in a second, of x of z times z to the n minus 1 dz. If you're not used to looking at an inverse Z transform relationship like this, let me just indicate that it's surprisingly easy, or it's surprising how easy it is to verify that in fact this is the inverse Z transform relationship, basically using the Cauchy residue theorem. But this is it. This is, of course, a complex function. This is a complex integral. And the important thing to straighten out is this contour C. The contour C is a closed contour in the z-plane which encircles the origin. So it's a closed contour, encircles the origin. It's like a circle that goes around the origin, with another very important condition on it, which is that it lies inside the region of convergence of x of z. Well, that's not surprising, because the region of convergence for x of z is the only place where we're allowed to stick in values for z. So obviously, quote, we're not allowed to look at values of this integrand except where x of z makes sense, that is, except in the region of convergence. So obviously then we have to evaluate this integral considering only values of z inside the region of convergence. So the contour C is a closed contour in the z-plane, encircles the origin, and it lies inside the region of convergence. Now, for x of z, a rational function of z, which are the cases we've been talking about, this entire integrand is a rational function, and consequently, a contour integral of this type can be simply evaluated using the notion of residues. I'll state, and hopefully this is a property of complex contour integrals that you're familiar with, that the integral of a rational function of that type, the integral itself is 2 pi j times the sum of the residues inside the contour. And that 2 pi j cancels out as 1 over 2 pi j. And consequently, x of n is simply the sum of the residues of x of z times z to the n minus 1 at the poles inside the contour C. The poles of what? The poles not of x of z only, but the poles of the entire integrand, that is, x of z multiplied by z to the n minus 1. Important point, which it's important to keep in mind. The integral, or the residues that we're looking at, are the residues not just of x of z, but x of z multiplied by z to the n minus 1. Another statement, just tuck it away, is that this is valid for both n greater than 0, n equal to 0, and n less than 0. We'll see in a minute that for n greater than 0, it might be easier to evaluate than for n less than 0, depending on the example. But tuck away the fact that this expression is a valid expression no matter whether n is positive or negative or, of course, 0. All right, let's look at the mechanics of evaluating the inverse Z transform this way. Let's return to the example x of z equals 1 over 1 minus a half z to the minus 1 with a region of convergence, the magnitude of z greater than a half. And by the way, by now, if there's one thing you should have gotten out of these lectures, it certainly should be to be able to recognize what the inverse Z transform of this is. It's an example that I guess we've bounced around so many times. All right, let's look at this Z transform. First, let's just look at x of z in the z-plane. Here's the z-plane. We have a pole at z equals a half, and we have a 0 at z equals 0. Here's the unit circle, and in green what I've indicated is the region of convergence. Now, to do the contour integration, it's not just x of z that we're looking at. It's x of z times z to the n minus 1 equals z to the n over z minus a half. Incidentally, what does the contour of integration look like then in the z-plane for this example? It's a closed contour inside the region of convergence and encircling the origin. So, for example, it's a contour that looks like this. And incidentally, it is, and I don't think I've stressed this before, it's a counterclockwise contour. So this is the contour C. It's a counterclockwise contour. As I've drawn it, I didn't draw a very good circle, partly because I can't, but in fact, it also emphasizes the fact that it doesn't have to be a circle. It just has to be closed inside the region of convergence, encircling the origin, and a counterclockwise contour. All right? How many poles of x of z times z to the n minus 1 are there? That is, how many places are there that we have to evaluate residues? Well, let's look first of all at n greater than or equal to 0. This doesn't introduce any poles. This introduces one pole at z equals a half. So we only need to evaluate the residue of this at this one pole, that is, at z equals a half. So we want to compute the residue, then, of x of z times z to the n minus 1 at z equals a half. So that's z to the n over z minus a half multiplied by z minus a half, evaluated at z equals a half. These two cancel out. And we end up with simply a half to the n. So for n greater than or equal to 0, the sequence x of n is just a half to the n. So that's part of the result. Now we have to get the inverse Z transform for n less than 0. Well, for n less than 0, again, of course, we have one pole at z equal to a half. But now, remember that we had this factor, which was z to the n. And for n negative, that introduces poles at the origin. And in fact, it introduces n poles. So for n less than 0, we have not only this pole, but we have n poles at z equals 0. That's a problem, because now we're going to have to evaluate the residues at each of these poles, and the more negative value of n we're trying to get x of n for, the worse it gets, because the higher the multiplicity of the pole. All right, but look, we've seen this example before. We know that x of n is a half to the n for n greater than or equal to 0, and it's 0 for n less than 0. That is, we knew that from other times that we've worked this example. So obviously there must be some easy way to get the fact that x of n, in fact, for this example, is 0 for n less than 0. All right, let's take a look at an easy way. Here we have, again, the inverse Z transform. X of n is 1 over 2 pi j times this contour integral. And let's simply make a substitution of variables. Let's make the substitution of variables z equal to p to the minus 1, in which case z to the n minus 1 is equal to p to the minus n plus 1, which means, incidentally, that with z equal to r e to the j theta, p, this new variable, is 1 over r times e to the minus j theta. So now we want to make this substitution of variables in this contour integral. Well, let's see, dz is minus p to the minus 2, just differentiating this. Well, I'll let you go through the algebra on your own, but if you take this substitution of variables, stuff it into that contour integral, then the result that we end up with is that x of n is equal to minus 1 over 2 pi j, the minus coming from the fact that dz is minus p to the minus 2 times dp. That's that minus sign. X of 1 over p times p to the minus n minus 1 dp. And what happens to the contour? Well, the contour previously was, let's say, r e to the j theta. Let's take it as a circular contour. So the contour now is 1 over r e to the minus j theta. That means, as one consequence, that our old counterclockwise contour turns into a clockwise contour. So that's what I've indicated here. But we also have this minus sign. And we can use that minus sign to change the direction of the contour. So if we change the contour back to a counterclockwise contour, get rid of the minus sign, then finally we have the expression x of n is 1 over 2 pi j times the contour integral of capital X of 1 over p, p to the minus n minus 1 dp. And what is this contour now? Well, if the old contour, C, was circular with a radius of r, this contour, C prime, is a circle with a radius of 1 over r. Well, let's just look at what this substitution of variables z to 1 over p did, as a matter of fact. Here, I've illustrated the z-plane. Here, I've illustrated the p-plane. The unit circle in the z-plane, when I replace z by 1 over p, turns again into the unit circle in the p-plane, because the unit circle is where the magnitude of z is 1, and if I take the reciprocal of that, the magnitude is still 1. The important thing is what happened to this contour. Well, this contour got converted, if it was outside the unit circle, into a new contour which is inside the unit circle. And in fact, in general, stuff that was in here, the inside of the unit circle, is going to end up outside the unit circle in the p-plane, and things that were outside the unit circle in the z-plane are going to end up inside the unit circle in the p-plane. This transformation simply takes stuff outside the unit circle and folds it inside the unit circle, takes things inside the unit circle and folds them outside the unit circle. And it's just simply a substitution of variables. All right, now with this substitution of variables, let's return to the example that we've been working. We had our example. X of z is 1 over 1 minus a half z to the minus 1. The magnitude of z greater than a half. We want to replace z by 1 over p, so we want x of 1 over p. X of 1 over p, then, simply replacing z to the minus 1 by p, is 1 over 1 minus a half times p. If this was true for the magnitude of z greater than a half, then this is true for the magnitude of p less than a half. So we get minus 2 divided by p minus 2. If we look at this in the p-plane, we have then a pole in the p-plane. The pole in the z-plane was at z equals a half, so the pole in the p-plane is at p equals 2. That's now outside the unit circle. The region of convergence now is inside the circle of radius 2. And where is the contour of integration c prime? Well, that now is inside the circle of radius 2. For example, let's draw it here. So this is now the contour c prime. All right? We want finally to evaluate the inverse z transform, or the inverse p transform, by looking at the residues of x of 1 over p times p to the minus n minus 1. The residues of that at its roots, at its poles, that are inside the contour of integration c prime. Well, for n less than 0, we have one pole at p equals 2, and for n negative, this will contribute no poles. Therefore, there are no roots of this inside this contour, and consequently, the contour integral is obviously 0. So x of n is equal to 0 for n less than 0. Now, for n greater than or equal to 0, we have one pole at p equals 2. But then, because of this factor, p to the minus n minus 1, we have n plus 1 poles at p equals 0. So now it seems like for n greater than or equal to 0, we're back where we started from, because now we have these multiple order poles at p equals 0. What do we do about that? Well, we don't have to do anything about it, because we already considered the case for n greater than or equal to 0. In that case, we didn't run into multiple order poles at the origin. We use this substitution of variables z equals 1 over p to basically avoid that problem and to get the answer for n less than 0. So consequently, the answer that we get, which we finally know to be the right answer, in fact, is that x of n is equal to 0 for n less than 0. And as we worked out before, x of n is equal to a half to the n for n greater than or equal to 0. Or finally, x of n is equal to a half to the n times u of n. All right, that's an example we've worked out now 3 times, and 3 times we got the same answer, so it must be right. All right, well, this roughs out the inverse z transform, several methods for getting the inverse z transform. Obviously, to become fluent with the inverse z transform requires working a lot of examples, and you know where you're going to have all those examples to work, that is in the study guide. And you'll find, as I stressed previously, that as you work more and more examples, what you find in computing inverse z transforms is that more and more frequently you're able to recognize the answer. Well, in the next lecture, we'll complete the discussion of the z transform. In particular, we'll, among other things, present some properties of the z transform, which also, by the way, help us in computing inverse z transforms. And so in the next lecture, we'll be continuing the topic of the z transform and, in fact, concluding the topic. Thank you.